Awesome. Well, thank you so much for inviting me. I would love to be there because it's really cold here. We've got the first frost of the year here in the UK. I can't complain. I live in the UK, right? The weather's better than it is in Denmark. I'm just going to say that right up front now. But yeah, it is. There's a nice thick frost outside, so which is why I'm all kind of wrapped up warm. I'm starting to feel Christmassy. So as much as I'd love to be with you in a nice warm theatre, I'm stuck here in a little cabin in my back garden, which in the summer months is lovely. But anyway, we're here to talk about, actually here to talk about language and definitions and meaning, which is it sounds a bit rubbish because it's supposed to be talk about technology, and it is also about technology as well. But basically, software is created by people talking together. So I think a discussion today about what words mean and how we communicate, and trying to get to the heart of a very common distinction that we like to draw in computing, and how that distinction doesn't actually make a lot of sense. Now, I've spent a lot of my time talking about architecture. And we know what architecture is. We're talking about, of course, boxes and arrows. And sometimes I'm talking about, this is what we can distill down a lot of our job as being when we're talking about system architecture. It's boxes and it's arrows. And sometimes I'm talking about how big the boxes are, right? I had a lovely workshop with some of your colleagues. We got to talk about how big things should be, or how small things should be. Other times we're talking about more interesting things, which is how do we take one box and break that box up into smaller boxes, which is also fun. Sometimes we also talk about what shape the boxes should be, and I'm very firmly in the camp of Team Hexagon. Team Hexagon represents, because it's a better shape. It's also good subliminal advertising. If you haven't got a copy of my book, it is available now from all good bookshops, although the background cancellation is kind of taking that out. But this is important, right? I've got a mortgage. But really, a lot of the conversations often about the box itself, but I think when it comes to microservice architecture, especially in other types of system architecture, often the most interesting thing is how those boxes communicate with each other. So it's the nature of the lines between them. It's how do these things actually get connected and how they communicate. Now, in the context of, say, a microservice architecture, which is something I spend a lot of my time talking about, we sort of, when we look at these arrows, and certainly the way I draw these arrows in these diagrams, I want to be very clear about what I tend to show here. What I'm basically showing here is a form of logical dependency, right? So I'm saying that one thing is dependent on another. So in this example here, I'm saying that like the returns microservice, it has some logical dependency on shipping. It needs to use functionality that the shipping microservice provides, okay? And that's what I mean when I draw these lines. Now, a lot of the distinction in the discussion about how these things should then communicate then starts becoming about a discussion about should things be synchronous or should they be asynchronous? And I actually think, unfortunately, although this is where the conversation often starts, I think this is deeply problematic, because I think when you get down to it, I'm not actually convinced that there's any consistent definition about what asynchronous means, which by definition then makes this discussion about which approach you should use quite difficult to have, because you may well be finding you're having a conversation with other people where you're talking at cross purposes. And the inspiration for this talk, which was to try and dive into the meaning of this distinction, and specifically looking at the word asynchronous. What does it mean in computing? And I was basically inspired to do this after reading a great blog post by Pat Helen. So some of you might be aware of Pat's work. He's very well known in sort of distributed systems circles. Spent most times working around the sort of database and transactionality as well. And he wrote this great piece on his Substack a couple of years ago now, which is refined since, where he was basically sort of discovering or reevaluating the term eventual consistency. And in this article, he makes the argument that we should stop using the term eventual consistency, partly because we use the term consistency in so many different places, and we use it to mean quite different things. So the consistency in eventual consistency is quite different to the consistency in, say, an ACID database transaction. And yet we're often still talking about these things very close together. So he comes up with the concept of calling this thing eventual convergence instead. And there's a great bit where actually the person who came up with the term eventual consistency says, yes, I should have called it eventual convergence. So I was hoping to have my own Pat Helland moment. I'd been struggling with the term asynchronous as to what it meant. And I thought, maybe there's a better word out there that we could use that would help clearly articulate what it is. And this is me up front explaining that I failed in that attempt. However, I want to take you through that journey, kind of where I've got to, and kind of a realization, to an extent, as I've been doing this talk about a year now, that only started to really crystallize about a month ago, that actually we can't have a new word because we actually probably need to have multiple different words to talk about what we mean when we talk about asynchronous computing. So I started trying to tear this thing apart. I was working on the second edition of my book, and I realized that when reviewing all of this stuff that I needed to beef up my understanding about asynchronous communication, and not so much what I thought I meant by it, but what other people do. When you sit down to write a book or explain concepts, the goal is always, can I help articulate meaning? And so I realized that I was using these terms without really checking what other people thought these terms meant. And so what I often do in these situations is I have friends. I promise I have friends, honest. Some of them will even consider that I'm their friend as well, but that's not always the case. But I also know people who are considered experts in this field, and I sort of spoke to them, and I sort of reinforced that by just reaching out on this. There used to be this great social network that was really useful for having good conversations. It was a fairly, as a white straight male, it was a fairly safe place to be. And that was a place called Twitter, which doesn't exist anymore. And so on Twitter, I went out and said, I'm a bit confused. What do you think asynchronous communication means? We're talking about inter-process communication. So I did set the context here, and context is important. We'll come back to this idea of context later. And I said, what does asynchronous communication mean to you? And this kicked off a flurry of responses, which I found really interesting and kind of form the basis of my exploration through this talk. Because some of the, and I want you to maybe think in your heads right now what asynchronous means to you. And then we're going to go through some of the responses I got and some of the other sources of information I looked at, because I think this might unveil some interesting observations. So when I put this original tweet out, this would have been 2021, and I got quite a few responses over the days following. One of the earliest responses I got was from Darren Hobson. Darren was actually an old colleague of mine. And so, he came back and said, well, for him, asynchronous communication with inter-process communication, it's a bit like the difference between sending an email versus having a phone call, which is sort of interesting, right? Because that feels like a kind of an interesting distinction, right? If you think about it, if I want to get an answer straight away from somebody, from a human being, actually picking up the phone and having a conversation, and as difficult as that might be for people like myself who would rather do everything via text if I can, that might be the fastest way to get a resolution. If I can get hold of that person, we can resolve the issue now and move on with it. Sending an email is often useful, but I may not get the response as quickly, there's a distinction there. Although there is, though, when we take that kind of distinction in terms of human communication makes sense. But when we apply it to computing, it does therefore imply that if we take Darren's definition of asynchronous, that asynchronous communication between services will therefore be slower, which we know isn't the case. And I've worked in fact, most of the latency-sensitive computing environments I've worked in rely heavily on asynchronous communication mechanisms. So that distinction is sort of there, but also doesn't feel quite right. But there is something useful, there's something interesting there. So while Darren, I was thinking about Darren's responses and other tweets were coming in, I started looking at other sources where people had made the ill-fated decision to actually write down their thoughts about what they thought asynchronous means. It's always dangerous when you write something down, because it allows people like me on the internet to then look at what you said and say, no, that's wrong. And so what I reverted to one of my favorite pieces of technical dogma, which is the reactive manifesto. So I'm going to say up front, right, the reactive manifesto, there's some friends of mine who I know multiple people that wrote this. I know a lot of people that signed it. I also frequently like beating it up for being a bit nonsensical, right? Because there's some good ideas in here, but it takes a fairly extreme view about how the world should do things. And at the same time, is quite vague to the point of not really being something that's actionable. I also want to be really upfront and say the people put a lot of hard work into trying to articulate their thoughts, and that should always be lauded. So please take me kicking it with a very huge pinch of salt. I'm doing it partly for effect here, but they have actually made the attempt in the reactive manifesto to define asynchronous communication. And I thought, well, actually, this is great, right? Because like I know Martin and Dave and people, and they're super, super smart people, and I've learned loads from them. So I thought, well, if they've taken the effort to define asynchronous communication, then I'm also going to learn from that as well, right? So let's look at their definition. So I've highlighted that for you. So what we've got here is, if I can get this thing to work, here we go. So we go through, and we'll look at the highlighted bit. I'm not going to read the whole thing out. So in the context of this manifesto, and again, setting context for terms is always important. In the context of this manifesto, so we mean that the processing of a request occurs at an arbitrary point in time, sometime after it has been transmitted from a client to a server. So this is defining asynchronous communication. And I'm sitting there and reading along, I'm nodding. They mentioned the Oxford English Dictionary there. We'll get back to the dictionary later. But it's like, okay, right, that sort of sounds right. Then I started parsing the words and thinking about meanings, and I read it a couple more times, and I read it another couple of times, and I'm thinking, okay, well, the processing of a request occurs at an arbitrary time, sometime after it has been transmitted from the client to the server. So after I've sent it, then it can be processed. After I send it, then it can be. Hang on a minute. What's the what as opposed to what exactly here? As opposed to being able to process the request before it was sent, like they've got some kind of Doctor Who networking protocol going on, where there's like a TARDIS wormhole, where this. So that already doesn't make any sense to me, right? Because, well, it always has to be processed after it's sent. Otherwise, you know, the causal nature of the universe is now under question. Now, to be fair, looking elsewhere, we find a more useful definition of what they think asynchronous means when they're actually talking about synchronous communication. So synchronous communication, they say, they're basically saying this is the opposite of synchronous communication, which makes sense, asynchronous being the opposite of synchronous. And they're saying that synchronous communication, the client only resumes its own execution once the service has processed a request. So this is what the Reactive Manifesto defines as synchronous communication. Okay, so this is actually a bit more explicit, and we can work with this term a bit, this concept a bit. The client only resumes its execution once the service has processed a request in synchronous processing. Right, and this actually chimed in with some of the other contributions on the Twitter thread. Right, so I had Steve Smith, another old friend of mine in the UK. He does a lot of work in the area of continuous delivery, works for Equal Experts over here. And you know, he initially came back and Steve said, okay, there's a TCP connection is open for the duration of the communication. And it was good because Steve was one of the first people that started talking about a lower networking protocol level. So he's like saying there's going to open a connection, and that connection is going to be talking to your computer. And for the duration of the communication, we've basically got a fixed kind of network link between the two of us. And so, of course, I start poking. Does it have to? What if I use UDP? Or what if I use Quick? Does that count? And Steve, well, actually, what Steve really said he meant, well, what I really meant was, I don't think you're blocking for a response. So this is actually using more specific language, which I think is useful. This is back to what the Reactive Manifesto talked about. So what the Reactive Manifesto talks about when it's talking about asynchronous communication is primarily talking about this concept, and that's non-blocking. So non-blocking calls, I think, are a very useful thing to discuss. And synchronous or asynchronous aside, whatever you think, I actually think non-blocking, where you can do it, is a very, very sensible thing to do. So let's talk about what that is. So we'll do a very simple scenario here. We've got a service called enrollment, and the enrollment microservice needs to make two things happen. They don't have to, they're not causally linked, these two operations. They're just two things that need to occur. One of the things is we need to go to the loyalty service and award you some points. And we also need to upgrade your subscription. Now, we don't have to do them one after the other, but that's just how they tend to be implemented, right? We've got a piece of code that implements these interactions. And as normally, most of us have been learnt to program, we write a piece of code, one line of code executes, the next line of code executes, the next line of code executes, right? The code just runs through in a linear fashion. And so in this example here, we've got loyalty service.award points. We can imagine we've got some kind of abstraction over our service calls here. This might be using, say, an RPC layer, maybe we're using gRPC under the hood, or maybe it's just a wrapper, sort of this is sort of an RPC style wrapper, effectively, a REST or whatever it might be. So when I execute this line of code, what's going to happen is that line of code is going to block and wait until the service request is sent, processed, and the response is sent back. So once that service call completes, that res1 is now going to contain the response of that call. We're then going to move on to the next line. Now, obviously, I've removed the kind of, the other kind of checks and guards that you would expect here. I haven't got information here around things like, retries and timeouts, but you can kind of assume that that's been dealt with, right? So once that's completed, then we can move on and make our second call. So we're executing, blocking, waiting. We're opening a network connection, sending it, block, wait, receive response, close. We go on to the next one. And so we go into the next response, and now we can send that next call. So this is a fairly straightforward implementation. This is pretty much commonly what most people will do the first time they're asked to do something like this. And I don't think there's anything inherently wrong with starting in this approach. The issue with these calls blocking, though, is what happens when it comes to things like latency. When you've got multiple operations like this, which are not causally linked, where you don't have to do them sequentially for processing reasons, you end up increasing the overall latency of your operations. The latency of this operation is now going to be bound to be the sum of the latency of the calls to the services. So if we might imagine that award points took 50 milliseconds and upgrade subscription took 150 milliseconds, we're now in a situation where we would look at that operation taking at least 200 millis. And obviously there's whatever else the enrollment service has to handle in that situation. And this also gets worse when you consider the fact that, of course, latency isn't fixed. You have variability in your latency. Both the calls to upgrade subscription and award points would have variability. And so when you're multiplying those, you're sort of summing up those latencies, you'd end up with a wider distribution of your latencies, which is an absolute pain when you're trying to do things like eliminate tail latencies or tune timeout frequencies, times outs appropriately. So it's not great, right? And there's another thing, which is, sure, it's always nice to be, you might say, well, actually, I don't care if it takes that long or not. The other thing to remember is the longer calls take, the more time you've got connections open for, the more resources you're building up, and actually, you'll also find you can therefore take and handle less load. So being able to do things quickly is also about keeping your system stable as well. Now, an obvious improvement in this situation would be to do both those calls in parallel, and that's what some kind of non-blocking abstraction would allow us to do. So rather than executing one line of code and then the next line of code, an improvement would be to say just execute both of those calls at once. Now, back when I first started programming, this would then involve me probably trying to play around with semaphores and sort of concurrency code in Java, which would inevitably result in me deadlocking the program, because that's what I could do at a drop of a hat. I could deadlock a program by looking at it. Nowadays, of course, we've got better abstractions, right? We've got the reactive extensions that we have in all programming languages nowadays, which make these kinds of sort of almost like background parallel execution much easier to establish. So in this example here, what I've done is I've wrapped effectively those service calls in a future. So a future is a read-only type, the value of which is going to depend on a potentially pending operation. Different reactive extensions will give you different abstractions around these sorts of things. So the key thing here is that when that line of code executes, so when that first line of code executes and the control flow moves on to the second line, it doesn't mean that the first service call has completed. What's in the parameter of that future is basically being packaged up and is being run on a background thread. At least that's how that would work in .NET or in Java, right? So behind the scenes now, you're going to have a thread where that network connection is being opened and the call is completed. So now effectively what we're going to have is those calls will be happening pretty much in parallel at this point. So this is great because that should bring down the overall latency of the operation from being the sum of those calls to now being the max latency, which in the example we had would take us from a 200 millisecond to a 150 millisecond type response, which just seems like a nice win. So straight away, in situations where you can do multiple calls like this, non-blocking calls seem like a no-brainer. There are other interesting ancillary benefits to things like these reactive extensions as well. In general, if you can build your systems like this, the code will stay a bit more lively. If this application had a user interface, it might be easy for the user interface not to get blocked. There are also other things to consider in terms of the use of multi-core systems. It used to be that Moore's law dictates that transistor density doubles every 18 months. Back when I was a child, that basically meant clock speeds doubled every 18 months. Our programs would just get faster because the computers got more powerful, because the CPUs were just getting faster. That stopped quite a while ago. And transistor density has resulted not in the top line CPUs getting faster, but actually us now having more cores. So to take advantage of that, having multi-threaded programs makes a lot of sense because then you can run these things on separate cores. So there's some interesting potential benefits there. And obviously, this is a very naive example of that. But if you take it to that logical conclusion, there are some significant benefits to programming in this way. There's a problem with all this idea, though. So we might now say, OK, well, this is now non-blocking. So this is now non-blocking. So we are now in the worlds we think of what the reactive manifesto meant. We are now asynchronous, which means we get a tick, a badge from them. And what Steve says, non-blocking, great, we're doing good things. But actually, let's stop there for a moment because we're non-blocking, right? But what if we need the responses? What if you need to know it worked? What if you actually need the answer of a service call to do something else? So that creates an interesting challenge, right? So in this situation here, at this point, if we're thinking about our code execution, at that point, we don't know if those calls, those services have actually been processed or not. We don't know if those calls are completed. We don't know if we've got a result or not. We just don't know. But we may need the answers. I might just want a simple acknowledgement that this thing has completed. It may be that I'm actually going to get back a new subscription ID, for example, when I upgrade a subscription, and that ID is now needed for some other processing that I'm going to kick off. When awarding points, I might get back an updated point value that I might need for some other processing further down this piece of code. So what do I need to do at that point? Well, if I need the results of these potentially pending operations, I now need to wait for the results. How would I wait for the results? I would use something like an await. Now, often in reactive extensions, you would combine all these activities into doing something like an async await. What does an await do? It blocks. The await sits there and says, let's wait until these operations complete. So now we've gone from non-blocking to blocking. So even if you want to have non-blocking calls, the logic of your processing may require that you wait for things to happen. This is another way of saying that even non-blocking calls may end up blocking. Now, So this is not obviously some magical panacea, because ultimately, if you care about the results of these things, and most of the time you do, you're still going to end up needing to block somewhere. It's still worth doing, and it's still absolutely worth running these things in parallel. Another thing you can do as well, by the way, around this stuff is to make it as easy as possible for developers to understand what's happening on the network. Often we work with abstractions over our network calls, which I think is completely appropriate in a lot of situations, but we do need to give people visibility. Using things like getting developers familiar with things like distributed tracing early on can be useful. So allowing them to pop up a simple, like, honeycomb or Jaeger view of their service interactions could help them see when calls are happening in parallel or not. So that can be a useful thing to help understand where these things are used. So blocking, non-blocking, okay, that's part of it, but there's other definitions for asynchronous out there. So I thought, let's dive a bit deeper. Here's Graham Lee, who came back with a response just after Darren did. And Graham works, Australian architect, works a lot on for a bank and payments company called Tyro out there, quite a complex microservice architecture. And Graham came back with this response. And he says, well, look, the definition I've been using is that the sending service doesn't wait for completion of the receiving services before continuing and or completing its own work. So that first sentence from Graham is absolutely, again, non-blocking. So that was good. I was starting to see commonality that for a lot of people, asynchronous means blocking, non-blocking. Great. But then he goes on to say, but now the more I think about it, I also expect a temporal decoupling from the service's availability. Now, this is a new thing that's coming into our discussion now. And this was also chimed in by other people as well. So Benjamin came back and said, well, look, I think that synchronous communication is a direct communication between sender and receiver. So this is back to our idea of open a network connection and I talk to you, which is also kind of not quite also it's not exactly how TCP works, but, broadly speaking, right? But now, again, Benjamin's saying, but I actually now think you have an intermediary here. That for Benjamin, asynchronous means there is going to be an intermediary. Now, nothing about the Reactive Manifesto talks about the need for intermediaries. It's mostly about non-blocking. So what is this thing? A message broker. A message broker. Well, what we're talking about here is something that sits between the client and the server, right? And this is where the digital message broker will sit in. So now we've changed the game. So now what we're going to have is service A. If I want to send something to service B, I generically talk about things that go on message brokers as being messages, right? They could contain request, response, events, whatever else it might be. So if I want to send it to you, I now send it via the broker. And the idea here is coming back to something that Graham touched on, is this temporal decoupling. So temporal coupling is what occurs when basically if service A wants to talk to service B needs to be available for service A to do its job. And that's temporal coupling. Well, to be clear, again, temporal coupling has different definitions in different contexts. But in the context of inter-process communication, we say that a service is temporally coupled if you need it to be available for you to complete your own operations. And so if I didn't have an intermediary and service B was unavailable, I wouldn't be able to complete my own operation. And that now means your service's availability is tied to a different service's availability. When we use an intermediary like a message broker, we avoid that problem, because now I can pass my message to the message broker, and the message broker can deliver that message to the other service when it becomes available. In effect, what we're doing now is we're offloading the requirement for guaranteed delivery to the broker itself. Although I'd say that's depending on your definition of what guaranteed delivery means and the message broker and how you set up the message broker. There's some kind of more vagaries there. So this is a different thing, right? This is a different form of asynchronous communication now. We're primarily concerned here about removing temporal coupling, and we're using an intermediary to deal with temporal coupling. Whereas before, our concern was about program execution blocking and latency buildup, and so there we were looking at the difference between blocking and non-blocking calls. And actually, probably the most popular kind of view of asynchronous communication on the response I had coming back was around these ideas of effectively the message broker. So this person came back and said, asynchronous is like dropping a mail in a post box and then going on with your life. And then boom, one day, Postman Pat stuffs something in your house mailbox, along with millions of coupons and charity mailers. So again, there's kind of a combination of ideas here. I've got this intermediary thing, the post box going on, in combination with the it might come back later on, that sort of late delivery type idea. For those of you who don't know, because I'm aware that although in the UK he is a major cultural icon, but I don't know how well Postman Pat translates. This is Postman Pat. This is the original OG Postman Pat. It was like a stop motion animation, and there's his cat Jess. The new Postman Pat, I think, has a hovercraft and stuff, but I think change has come way too. I live in a village like the one that Postman Pat theoretically works in. There are no hovercrafts here. But so mailboxes, right? This idea of the mailbox and the mail delivery service as a metaphor for message brokers can be really useful. So I'm in my garden. There's a front door at my, over there. I'm pointing to it. I don't need to be at my front door for letters to arrive. Letters get put in my post box and I can pick them up. Obviously, in America, you don't get to do that. You have to have mailboxes at the end of your property, because if you come onto the property to deliver the post, someone will shoot you. But we all have the idea, right? There's a box that's going to hold our stuff for us, and when we're ready, we can pick it up. If I happened to be at the front door, I could take it straight away, but I could get it after my coffee, after I've had a lie-in, after I finished this presentation, whatever. And that's really useful in a services context, because now what we're doing is we're giving our services the opportunity to not always have to be available for the consumers of that service to still be able to operate. So A talking to B, A can still carry on operating even if B is temporarily unavailable for what could be really good reasons, like we're deploying a new version of it, for example. The message box is going to hold on to that work until it's available. And there are different ways we can implement this sort of inbox pattern. Brokers are by far and away the most common way of implementing this. I'll take that back. Brokers are the obvious answer we come to when implementing this pattern, because brokers have lots of great capabilities in them that make this easy. Keeping track of consumer state, for example, being key amongst them. But actually, people implement this pattern a lot without realizing they're doing it, using other mechanisms. Some people use databases for this. So if you're doing a system where you've got loads of services talking to a big database, right, often what's actually happening is one service is putting some data in a database, and later on a different service is picking that data up, right? You're often using a database or tables in databases effectively like a message broker. In fact, Oracle sell a messaging product, which is just a wrapper on a database table, because they're Oracle, everything's a database table, right? But people use files. This is probably the single most common system integration technique in the world, right? Is one program puts a file in one location and a different program picks it up later on. So here we're using the file system to hold on to our content. Still obviously inherently a distributed system, because we're probably relying at this point on things like NFS or ZFS or alternative distributed file systems to make that work. You could even use email for this, but you shouldn't, so please don't. But the brilliant thing about this type of asynchronous communication is the sender of the message does not need to worry about whether the recipient is currently available or not. However, you are going to have to trust the intermediary, because that does need to be there. That does need to work. And so the reason brokers are often attractive for this is because the people who build the message brokers are smart people who have thought about how they build a durable, highly available service to hold on to important things for delivery. That's why you shouldn't try and build your own message broker. And it's also, though, does lead to a degree of complexity into operating them. So if you are running the public cloud, using the public cloud's broker solutions is normally the way to go, rather than running your own solutions. But you all know the products that are in this space, and I know you're using some of them internally, so I won't go too much into that detail. So now if we think about classical kind of request response-based communication. So a distinction I tend to prefer in the area of microservices, which we'll come back to towards the end, is really talking about request response and event-driven, because I think that's a different mindset. But we could take that classical request response-based communication and apply that in the context of having now a broker helping us out with our work. Because this is often something that is a bit of a tricking point for people. People see events, I can understand how that works with brokers, but how do brokers work for request response? It's actually pretty straightforward, right? So in this example, A wants to send a request to B to then get response back. So A takes its request, puts the request in a message, and it puts it into a queue. So this would be B's request queue. And B, once it's ready and available, gets that request, processes the work, and at some point later on sends a response back that goes in a different queue that A can then pick up. Very, very straightforward. Yeah, it's just not rocket science, really. There's nothing that difficult about how this whole process works. This can be great if, this can be as good if things are taking, less, sub-second communication. This is absolutely fine. This can also work for things that take like 15 days. I worked on a system like this where we had asynchronous communication interactions that could take days. So it's fine, absolutely fine. Exactly how fast you can make these things is then a product of the broker using and a lot of other factors, but this can still be very, very good for quite low latency operations if you want. Now, this does, though, when we start looking into this world, open up a different set of challenges that we need to consider. Because so far, what I've been drawing my service diagrams, I've been kind of showing you things effectively as a logical architecture. I said there's a service called A and there's a service called B. But in reality, we recognize that it's quite common that we'll have multiple instances of these services. So just to expand a little bit, we could easily imagine that we might have two instances of service A. In fact, we might have more than that. Let's say two just for the moment. So I've got the first instance of service A, sends that request. B picks it up and processes it, and it then sends a response back. However, unless I do some extra work on top, there's no guarantee that the instance that sends the request is going to be the one that picks up the response. Now, often at this point, people say, oh, no, that's okay, because we'll do some fancy stuff in the broker to ensure that the service that sent the request is also the one that gets the response. Effectively, you're doing like you would do with sticky session load balancing, right? To which I would say, don't do that. It's an attractive idea, right? Because what you're saying is, I want the response to go back to the same service instance that sent that request in the first place. Why? Why do you want that to happen? Often the reason you want that to happen is because the first instance of service A, that top instance of service A, is holding on to state in that running service instance that it needs to have to be able to process the response. And if it went to a different instance, that different instance wouldn't know how to handle that response. So I've basically got maybe in-memory state, so I can pick up the processing and carry on with the processing. The fundamental problem with that, of course, is what happens if that instance dies? Well, then you can't handle the response anyway. So what you should do instead is build your system in such a way that any instance of service A is able to handle that response. That therefore removes the need for you to worry about directing responses to the right specific instance. It also avoids the need for having to it avoids completely the problem of worrying about what happens if instances die. Another solution people try and use here is doing like in-memory replication of state between your instances, which is just something you should never do because it's horrible. We can get into more detail about that later if you want. So, okay, we've got this idea now that A sends a request, but then it dies. The response then comes back to a different instance of A. That's great, makes it more robust. Great, but then coming back to our earlier example where we weren't using a broker, we do now have questions about this. What happens if it dies partway through? Because in this, explicitly, by the way we've written the code, the responses are coming back to the same instance. Because it's this instance that's opened up these network connections, and it's coming back to me. So what happens if that instance dies? What happens if the enrollment service dies and those responses just go nowhere? We have to think about how we handle that situation. Now, in practice, what you would do if that instance died, you just restart the whole operation. You'd redo those calls. Then, of course, you need to make sure those calls are idempotent, which is something you should always be doing anyway. And again, I could probably do a whole talk on idempotency because that's a much bigger conversation. But I do think it's kind of interesting here because fundamentally what we're talking about with this model here is basically encouraging stateless processing, like we do with REST, right? With stateless processing, we can get the entire, all the state we need. Have you lost the screen? There we go. With stateless processing, when I get a request, I can handle the whole thing from the same request before sending it back out. So I think it's arguable that using an intermediary, we actually encourage stateless processing, and stateless processing is always the best in terms of scaling and in terms of robustness. So we've got different things that are emerging here, just to sort of summarize where we're at. For some people, asynchronous versus synchronous communication is about immediacy. I don't think SE stacks up. I think it does when we apply it to the human world, email versus a phone call, but I'm not sure those distinctions make as much sense in computing. As I say, the majority of those low latency organizations I've worked in, the communication is inherently what some people call asynchronous. For some, it's about dealing with temporal coupling. Others, it's about non-blocking. And for some, it requires an intermediary to achieve that non-blocking. And it gets quite confusing, right? Like, which is the real asynchronous? Which is the one we should use? There's also a question we say here, does it matter, right? Does it actually matter? Words in English have different meanings. I mean, I think the majority of you in the room here probably did not start speaking English as your first language. You are probably therefore keenly aware that words in English often have different meanings. If I was in the room, I'd do this as a pop quiz. What words in the English language, or what word in the English language has the most dictionary meanings? Some of you might know this. It's actually the word set. Interestingly, for programmers, get is close behind. So it's nice that get and set both have. And in the new edition of the Oxford English Dictionary, which is scheduled for release in 2037, this is like the 60 volume, like this is the whole, all of the English language. So run is going to be the new word that we think is going to have the most meanings. Set has 430 meanings in the dictionary. Okay. Run is going to have 645. And that's at the current draft. Right, this could go up. So at the same time, it's like, yeah, I blow your mind. But the same, could you get you to write all 430 meanings of set? Absolutely not. Can you use the word set in normal conversation quite easily? Absolutely, you can. So we already deal with this. So what's the problem here? Why is Sam bugged by the fact that asynchronous means different things to different people when we already have words that we use every single day that have multiple meanings? And the reason this is a bit of an issue is because ultimately we derive our own personal understanding of a word via the context in which that word is used. And I had a great conversation with Ian Cooper about this. So some of you might know Ian's work. Some people have a hinterland, like they have other things they do in their outside their main job. Ian Cooper's hinterland is like the size of the Alps, because aside from also being, an expert in the area of message-driven communication, he also develops RPGs, and also, it turns out, has a degree in semiotics, which is the study of meaning. And he explained this to me. He said, the thing is, the meaning of a word we have, it becomes more narrow as we add other words around it. So as we communicate, the words around a given word give that word itself more explicit meaning to us. It narrows set down from the 430 meanings to the one that we want to communicate with. So to give you a concrete example, I want you just right now to think of the word run. What does run mean to you? Just one definition of the word run in your head. And I'm going to put some words around it, and we'll see if we were talking about the same word. Okay. The issue got worse the moment the program was run. So I'm using run with one definition. Was it the same one that you had in your head? Maybe, maybe not. Let's try again. Think of a different definition, a different meaning of run. Think of a different definition that run means to you. And I'll put some more words around it. We'll see if it matches up again. The economy crashed due to a run of the banks. Again, probably not the same meaning you had. But as I put more words around the word run, what I mean by run immediately becomes more meaningful to you, and you know we're now talking and communicating about the same thing. So this is kind of interesting. The problem with asynchronous is that we throw the term asynchronous around a lot without ever giving the context around it. And as a result, we say, should I use synchronous or asynchronous communication? We think asynchronous communication is best. Without other words around it, it becomes meaningless. We're using the term asynchronous out of context, and therefore the meaning suffers. Coming back to the Interactive Manifesto, the definition they use, that they pick from the Oxford English Dictionary, by the way, is they say the Oxford Dictionary defines asynchronous as not existing or occurring at the same time, implying that there is a single definition of asynchronous in the Oxford English Dictionary, which we know is not true. Now, I actually have access to the full Oxford English Dictionary, which is not that hard to get hold of. And if we go and look at the definition of asynchronous, that is indeed the first definition you see. That's also what turns up if you Google what does asynchronous mean. It's what Google tells you asynchronous means. It is only the first definition of multiple, and it is specifically a definition that was originally only used in medical contexts, and yet here we are using that definition to talk about computing. So is there a computing context? Yes, there is. In the Oxford English Dictionary, we can zoom down. There are actually two different definitions for asynchronous communication in the Oxford English Dictionary, and the one that's closest to what we're talking about makes no sense at all, but at least is a bit more meaningful than the one in the Interactive Manifesto we've used. Designating data transmissions in which packets of data are sent at irregular intervals, with the start and end of each packet being marked by specific signals involving such transmissions. Now, I don't know what that means. I understand some of the words there, right? This is clearly a definition of asynchronous. I suspect, and I can actually look at the citations to find out, I suspect this comes from discussions about networking protocols at quite a low level, and I would guess this probably even predates discussions around TCP. So this is an old definition, but at least is more contextually correct than the one we commonly use for computing. Look, this is all about meaning and communication. Right? Software fundamentally is a type of socio-technical system. That's a big word. I should define that word, shouldn't I? Socio-technical. Socio-technical means it's people and technology. And here when we mean technology, we mean like a sense of procedure and knowledge. This is the old kind of Latin definition of technical. This is people and technology coming together. And there's a whole study in the area of socio-technical systems. How do people and technology work together to deliver like proper insights? Okay. The amount of software created by individuals is vanishingly rare. It is people working together who create software, and therefore understanding how people can work well together is essential if you want to understand how to create good software together. Bringing people together requires to use a new technology, requires good communication. And I've just noticed a typo in that slide, which I think is ironic in a slide where I'm talking about good communication. Anyway, but what we were trying to avoid here is the problem where, you know, somebody says, we're going to make this thing asynchronous, and you've got a completely different view of what that means in your head, because that misunderstanding can lead to problems. And we've got precedent for this. Some of you might know the story of the Tower of the Babel from the Old Testament. And, you know, the people we now think of probably were the Babylonians, were building a big tower. And the Old Testament God said, oh, they're doing quite well with that big tower. I want to mess with them a bit. And so the people who spoke with one language were able to work together to build the building. It's actually a very short passage in the Old Testament when it talks about this. And what happened was God went, well, I'm going to make them all now speak different languages. And the whole thing fell apart. It's never exactly explained why God was doing this. There are interpretations. I do not want to get into interpreting Old Testament scripture at this point because I think that might take us off a wrong path. But this idea, even in the Old Testament, that one of the key things that made the creation of the Tower of Babel possible was everybody speaking one language. When you took that away, the enterprise crumbled. The problem we've got is that we use this term asynchronous without context. It has so many meanings, it is effectively meaningless. So what can we do about this? I think, to be honest with you, it starts by saying, well, what does our application need? Describe how it should handle different situations. Ask questions like, what should it happen? What should we do when the server is unreachable? How fast does our application need to be? What should we do if the client crashes? And where possible, use more explicit terms. Say things like, our client should be non-blocking. We should run operations in parallel where possible. We're going to use broker X as an intermediary. And for me, I think the two most important distinctions that come out of asynchronous communication is, intermediary-based temporal decoupling and non-blocking, right? And those are two concrete concepts that you can talk about and describe and discuss the merits of. Now, I don't didn't want this talk to be about just trying to correct everyone's usage of these words necessarily. It should all be about improving communication. In The Princess Bride, that running joke where Ingo Montoya is picking up Vizzini's word, the definition, use of the word inconceivable. The whole joke there, of course, is that he's using the word wrong and everybody knows he's using the word wrong. But we don't know that with asynchronous. We don't know that people are using the word asynchronous wrong. And that's the difference here. But just next time maybe someone says, we should make this asynchronous, or I think asynchronous is best, probably just the thing for you to do is stop them and say, what does that mean to you? And maybe the answer might surprise you. That's all I've got. I think we should have time for some questions. But thank you so much for your time. And thank you. So I don't know if we've got time for questions. I can't hear the microphone at the moment if there is time for questions, but.
Paul, you almost have a hand.
No, I can't see your face, so if it's a bad question, I won't know who asked it.
I don't think we have a question for you, Sam, but thanks
No worries.
For joining us.
None at all. And if anyone does have a question later on they wish to ask me, Morten, you've got my email address, so you can always just, send them over my way.
Sure. Thank you, Alan.
Take care, everybody. Have a great rest of the day.